nanomaterials laboratory, and I'm here only as a visiting faculty, and we are doing some work on these nanomaterials, particularly on photocatalysis. All of us know that nanomaterials, actually I would like to tell something about briefly about these nanomaterials, and then the principle of applications. Then I'll go for my slides. You know, all of us, that what are nanomaterials? The materials, sizes between 1 to 100 nanometer, they are called as nanomaterials. And there is a difference between, characteristic difference between the microstructure material and as nanomaterials. So microstructure materials, they have properties similar to the bulk materials, whereas the property change when the size is reduced to the nanoscale. And when the size is below 10 nanometer, they are called as quantum dots. So the property changes can be very well illustrated by the gold. All of us know that the gold is an yellow in color, but whereas it changes to red when it comes to the nano size, and the temperature, melting temperature also changes, and it also will not conduct electricity when it becomes less than 10 nanometers. And bulk gold and platinum are non-magnetic, but at nano size they become magnetic. And carbon nanotubes, they are very stronger. They have stronger electrical properties than steel, but its weight is only 1/6 of that, steel. So actually, nanomaterials play a prominent role in catalysis, particularly in the case of catalyst. What we require is a surface area. So when you take a nanomaterial, suppose for an example, if you take a cube of iron, 1 centimeter cube means the surface atom is only 10 to the power of -5%. Whereas if you take a cube of 10 nanometer edge, the percentage of sulfur atom is 10%. At the same time, with the cube of 1 nanometer edge, almost every atom is on the surface. Out of 27 atoms, 26 iron atoms are on the surface. So 93.3%. So the surface to volume ratio plays a vital role in the heterogeneous catalysis reaction. And that is why when you take a zinc oxide, the nano zinc oxide is more advantageous than the zinc oxide, bulk zinc oxide. So nanotechnology today, that the ANKURAN 2023, the theme is the nanotechnology and its applications. And what is a nanotechnology? Basically using these nanomaterials for the industrial purposes. So present and the future of the society, depends on the development of multifunctional nanomaterials. So nanomaterials, we have a lot of applications, and particularly they are, it is multifunctional. And basically, as Dr. Guru Prasad pointed out, it is an interdisciplinary subject. So when there is no material, no progress. So catalysis are the first nanomaterials with wide applications both in industry, research, academic research and industry. And particularly the photocatalysts are very, very important because they can make use of solar energy, and it's an eco-friendly, promising technology due to the low energy input and can sustainably convert solar energy into storable chemical energy. So the present research is focusing on the development of new nanomaterials or catalytic materials, and in the recent years. So we'll see the role of photocatalytic nanomaterial in energy and environmental applications. So you can see this slide after the fabrication of the photocatalyst. So the photocatalysis, what are the different fields it is applied? You can see the inner circle shows that that water treatment, self cleaning, anti-mist, smell elimination, and destruction of microorganisms and air purification. So these are the fields. Some of the fields which are used, photocatalysis is applied, and here you can see in the outer circle practical applications. How this, this nanomaterial can be used in the buildings or car, in that other hospitals or the highways and engineering and other people. So here the slide gives an idea about that field of application and the practical application of catalysis. So we'll see some about the principle involved in the applications and morphology of the photocatalysts that we developed. Some of the photocatalysts are developed, and the environmental applications, particularly the degradation of toxic chemicals or the effluent, treatment of the effluents, and some of the energy applications also. You can see this is a principle, involved in that photocatalysis. Particularly in the degradation of toxic chemical. You can see that any photocatalyst, if you take TaO2 or zinc oxide, And when you excite with the energy equivalent to the band gap energy, an electron from the valency bond goes to the conduction band. So an electron and a hole both are developed. An electron can react with oxygen forming superoxide radicals, or again H2O2 forming hydroxide radicals. Similarly, hole can react with the water and hydroxide ions forming the hydroxide radicals. So finally, what happens is either superoxide radicals or hydroxide radicals, they react with the intermediates, and then they can completely mineralize. They can react with the pollutants and forming the intermediate, and finally completely they are mineralized. And the bacterial decontamination is one of the, field which is used for the photocatalysis, and they have been shown to be effective method for removing the bacterial contamination. So TiO2 can kill the bacteria on the surface. Nowadays, at the hospitals and at the walls of the hospital, these operation theaters are being coated with paints containing TiO2 and other materials, so that the self cleaning will be there. And even the medical devices are, coated with these materials to have the self cleaning. So here, this is a principle involved. Actually, these radicals which are produced in the presence of light can rupture the membrane, so they can kill the bacteria. And particularly, this is very important in the future. Energy source is only hydrogen, and water, if it is split into hydrogen and oxygen, and the hydrogen is one of the very good fuel source. So here that even that 1972 Fukushima and Honda reported water splitting and by TiO2, titanium dioxide. So this actually here split the water into hydrogen and oxygen. So photocatalysis, as we see, has a wide applications, but we have to develop a photocatalyst suitable for a particular application. That is very, very important. So there are 3 reaction steps are involved. Basically the light harvesting is required, and charge separation is very, very essential, and generation and separation and catalytic reactions. For these 3 steps, the basic requirements are the catalyst should be visible light active, because unless if it is active in that solar light, we cannot make use it in the sunlight. So it should be visible light active, and the recombination should be reduced. Once electron and the hole they form, if they recombine, it is of no use at all. So we have to make use of the electron and the hole, then only we can have a good applications. And another thing that is required is a large surface area. So these are the 3 requirements to achieve the good property of the photocatalyst material. So how to find out? Because when you take TiO2 is UV sensitive, and even zinc oxide, the band gap energy is equal to that, nearly equivalent to the UV energy. So that is why we have to find out some catalyst which is very, very active in the visible light. So that is why what they do is semiconductor oxides are modified by doping with metals or non-metals or metal halides or anions, or even coupled with other semiconductor oxides, are sometimes loaded with surface active materials like zeolite activated carbon and other carbon materials. So this is actually, this slide shows, you can see that different modification techniques. We can have the metal doping or non-metal doping, or we can have co-doping, that is bimetallic doping, metals or a metal and a non-metal like that, and a composite also. Now, this nanocomposite has come to very, very prominently coming to the picture, because nanocomposites are very useful. And the thing is that what is a nanocomposite? Basically, it contains 2 or more than 2 components, but one of the components should be in the nanometer region. And if you take, some clay or other material, clay-based matrix, so clay or other things, that they have formed the basis, whereas other nanometer will be incorporated in the clay or the activated carbon or any other graphene oxide, other things. The matrix-based photocatalysts are really very good in activity, that is a degradation, and also for some other activities. So actually we have done some of the clay-based photocatalyst, and it is an innovative approach to improve the application of the heterogeneous photocatalysis. So some of the materials used for the development of matrix-based catalyst are the reduced graphene oxide, activated carbon, fly ash, and different types of clays. And again, there is a report in from 2011. One of that they proposed the formation of single atom photocatalyst. Actually, the single atom or single atom metal atom oxide, They have been prepared and then it is stabilized on some of the supports, some of the matrices. So that is, they are found to be very, very efficient. The single atom photocatalyst possesses actually some strength enhancing the light harvesting and also the charge transfer dynamics and surface reactions of the photocatalytic system. Actually, these are some of the examples for different type of dispersing single atoms on the supports. You can see that interacting the surface anchoring sites and subscripting the surface atom with the lattice matrix. And sometimes it is also possible to coordinate with the organic bridging ligands, or it can use metal organic primers to anchor the single atoms. But actually, the preparation, even after the preparation, the characterization requires a sophisticated instrumentation for the single atom photocatalyst. So since 2002, we had been working in the field of photocatalytic materials. So we started with simple TiO2 and zinc oxide. Later on, we prepared more than 150 photocatalysts, metal or non-metal doped or coupled oxide, all these things. And some 2 reviews have been published recently and some book chapters. Recently, we prepared some single tungsten atom oxide and single vanadium atom oxides. And characterizations are being carried out. And basically, the size and morphology of the photocatalysts play a vital role in its applications. You'll see some of the catalysts, their morphology and their applications in a fast manner. So these are the 2 reviews that we published in the 2014, a long back. So this is actually, you can see that some pictures of the nanocrystals of zinc oxide. So here you can see that the nanocrystals are very, very active and also anti-photocorrosive. You know that zinc oxide is very active as a photocatalyst only in the alkaline condition. So when the pH is 9, it is a very suitable pH for the zinc oxide to be very active. Whereas when you go to the acidic pH, it undergoes a dissolution. So it can form the zinc ions and oxide ions. So it loses its activity, photocatalytic activity at all. So that is why normally zinc oxide cannot be used in the acidic medium. It undergoes a dissolution. Actually, that is what we found out the dissolution rate of zinc oxide nanocrystals and also the dissolution rate of zinc oxide, commercial zinc oxide. We found that 0.6% is the zinc oxide crystals, whereas in the case of commercial zinc oxide, it is 3.5%. That shows that zinc oxide nanocrystals are anti-photocorrosive. They are more stable when compared to the zinc oxide, commercial zinc oxide. So this makes zinc oxide nanocrystal as an efficient. Actually, even at the pH of 7 or 6, we can use a zinc oxide nanocrystal. Whereas zinc oxide, commercial zinc oxide cannot be used as a photocatalyst at this pH. And another one that we reported earlier, that is silver TiO2. 1% silver TiO2, you can see here that is having the maximum higher absorption in the visible region when compared to the TiO2, or even actually 1% is an optimum concentration of silver to get the maximum absorption in the visible region. So this we prepared and then, and this is the morphology of this catalyst. And then we tried that degradation of some of the toxic chemical by using this silver TiO2. And this one also used with the clay for the synthetic organic transformations. I'm not showing here. So this is a chart images of this zinc oxide, silver TiO2. You can see the particle size distribution and these lattice fringes and side pattern to show the crystallinity of the catalyst. And this is a coupled oxide. That is bismuth oxide is zinc oxide. We got a very good morphology of this bismuth oxide, zinc oxide, nanofiber and nano chain-like structure. And this is very useful for the degradation of dyes at that time. And in the case of coupled oxide, the mechanism is the conduction band of the zinc oxide and bismuth oxide, they are, different. So that you know that any electron from the conduction band of zinc oxide can, transfer to the bismuth oxide. So there is a good separation of electron and the hole. So that is why it is more efficient due to the separation of electron and the hole. So this is another coupled oxide bismuth, coupled semiconductor, bismuth sulfide and zinc oxide. It also has a very good morphology. And here you can see the same mechanism and the degradation as some dye, acid black 1 degradation dye is shown here. And we prepared one catalyst called floating catalyst. Actually, you know that some of the pollutants are, floating pollutants are also there. Another thing is the floating catalyst is advantageous because the light can directly fall on this catalyst so that it will be more active. So this is the sunlight and other things. So we have prepared a TiO2 pawning, that is polyaniline composite, and it is incorporated on that cork. So this is, you can see, this is a cork. The cork, the TiO2 pawning is incorporated, and this is found to be very efficient in the degradation of the toxic chemicals, floating catalyst. Another one is, we also prepared some this silver bromide paper, hybrid paper silver bromide TiO2, and particularly it is very useful for the indoor air purifications. So this catalyst has an excellent ability to remove ethanol in the gas phase, which make this hybrid material effective to treat the polluted air. So it can also be used in the commercial applications as a deodorizing filter or indoor air purifications. And this is another nano composite. Actually, we started using that rare earth vanadates and rare earth tungstates. So this gadolinium vanadate tungstate zinc oxide bentonite material and used for the degradation. This is actually fly ash. So fly ash is a waste material that is obtained from thermal power plants. And in the Neyveli Lignite Corporation in our place nearby, we used to get the fly ash and characterize that fly ash, and then we prepare the fly ash zinc oxide. It is found to be 9% of fly ash zinc oxide is found to be very efficient in the photo degradation of some of the toxic chemicals. So this is actually reduced graphene oxide is another base matrix, and here this is a nano composite. And we used earlier we had been trying only these dye degradations, but later we started doing that degradation of this pharmaceutical compounds like ciprofloxacin, dichlorofenac, and ibuprofen, because nowadays you know that even if you send a paper with a dye degradation, the journal says no, it's not acceptable. So they wanted the degradation of CECs, contaminants of emerging concern, like that. So here this is actually RGO, that is reduced graphene oxide bismuth vanadate zinc oxide nano composite, and used for the degradation of the ciprofloxacin. This is oleum vanadate RGO zinc oxide at different magnifications. The images you can see a good morphology, and this is used for the degradation of ciprofloxacin, and is about 98% with the catalyst. And another nano composite that we have prepared is samarium molybdenate zinc oxide and RGO, and you can see that morphology and also the mechanism of this. And this is again dysprosium tungstate zinc oxide, and this is also a very good photocatalyst, and it has a different structures, very good morphology. That is a combination of sandwich mesoporous microstructures clustered together in this one, and this is also very useful in the degradation of the toxic chemicals. So this is actually the degradation is shown here. Only this rhodamine B degradation is shown here. You can see that this is very highly efficient when compared to the other catalyst. Okay, how to, this is actually a bench reactor. It's called a multi-lamp bench reactor, photoreactor. So here we take about 50 ml of solution, either it is a dye solution or ciprofloxacin, whatever the solution, and then we add this 100 milligram or 50 milligram of the catalyst, and then these are that actually center we have the reaction chamber, and outer we have this light and the cooling lamps are there. So by using actually we can use this either UV light 250 nanometer UV light or 365 nanometer UV light, or this visible light. All this can be used, and then every 30 minutes or 60 minutes we take the sample and then analyze it. And this is one which is used preliminarily to find out the suitable catalyst for the degradation of any toxic chemical, whether it is a dye or any other pharmaceuticals. Then we can hope for this pilot scale treatment. So this is another visible reactor, that is immersion reactor. So the lamp is immersed, outer we have the solution. So this can hold morely, actually this is fabricated one. This can hold about 150 ml of the solution, so that by this we can follow this degradation by using this tungsten lamp, visible lamp. Either we can use 300 watt tungsten lamp or 500 watt tungsten lamp. And this is the one we set up in our place. This is called a pilot scale solar photoreactor. So here it can treat about 50 liters of effluent, and any industrial effluent we can get, and then we can actually we have done only the dye solutions earlier. Later we were able to get effluent from some of the industries and treated with the catalyst. But for this one pilot scale, we cannot use the costly catalyst. We have to use the catalysts which are very cheap, because actually you can see the blue here. This is an acrylic sheet, and this acrylic sheet is coated with the catalyst. We require nearly 10 gram of catalyst to coat this one, and the catalyst is mixed with 5% of the Fevicol so that it will not come out. So this is the catalyst which is coated on the acrylic sheet, is coated with the catalyst, and the effluent is made to flow from the top, and this setup is made, it is flow evenly, and then you can control the flow also. So by this you can treat 50 liters of the effluent, and we have treated some of the effluents by using this, and these are the focus mirrors so that light will be focused on this. So this is some of this, that this is actually bench reactor scale. The bench reactor, we find out that which is a suitable catalyst. We have taken only TiO2 P25. Mostly, I think what is TiO2 P25. It's a mixture of two anatase, 80% anatase and 20% rutile. Is commercially marketed for environmental remediation. And zinc oxide, commercial one, Merck, and fluoride TiO2, zinc oxide nano, and this AC, activated carbon loaded zinc oxide. So we found that activated carbon loaded zinc oxide is found to be most efficient in degrading this, dark brown dye from the leather industries. And this, we have taken a dye effluent for the solar farm. This in the pilot scale photoreactor, you can see the dye effluent concentration is 6000 ppm, and we have used 3 catalysts: commercial zinc oxide, prepared in the sense nano zinc oxide, and TiO2 P25. With nano zinc oxide, you can see that 92% percentage of COD removal occurs within the time of 6 hours. I think that with this 6 hours we are able to get a 92%, and that is not our irradiation time. Sorry, 4 hours. So this is intensity of solar light, and we are able to treat the effluent by using our pilot scale photoreactor. So once you know that it is possible to remove in 4 hours, then you can go for the large scale treatment also. And another one is a pioneer gelatin industry effluent. Gelatin is obtained from the bones of these animals and all. So here most of the organic polycake compounds are there. So we have taken this industry effluent, and this 12,971 ppm, and by using this pilot scale, this wastewater contains lipids. So we have taken this effluent in our pilot scale photoreactor and used this TiO2, prepared TiO2, nano TiO2. We use the nano TiO2, and then we have treated this one. The percentage of COD reduction within 6 hours is 92.8. It was very, very, efficient in treating this one. That is, prepared TiO2 was very efficient. And these are some of these, reactors I have taken from these journals, and actually this is from the case studies. In foreign countries, they use all these reactors for the treatment of the effluent in the large scale. Whereas in India, we are not using it. India, no industry is coming prepared for using this our photoreactors for the industrial effluent treatment. And when I was working in Chidambaram, the nearby we have a industrial area, that is Sipcot, Kadalo Sipcot area. We approach the industries, but they are not even given this effluent. And unofficially, we got the effluent and treated and got some of the data, but we are not using it. So this are the plant, and this plant can be used. And even in the countries where that sunlight is scarce or less available, they are using this type of photocatalytic reactors for the treatment of the industrial effluents. And now we'll see something about that antimicrobial activity. This bacterial decontamination. This can actually, we have taken RGO, holmium-aminated TiO2. You can see that we have taken some 3 or 4 bacteria, and we found that very good interaction is there. You can see this activity that by INCI method, that 18 millimeter and all these things are there. So they are very found to be very active. Similarly, we have taken about 17 catalysts about 17 catalysts, 11 catalysts are found to be very active at that time. So these are the 11 catalysts which are active: zinc oxide, AgTaO2, and all these things. That short names are given here. Europium oxide, zinc oxide, all these are very active against two bacteria, Bacillus subtilis and E. coli, gram positive as well as gram negative bacteria. And now we will see this, indoor pollution, air pollution. The photocat oxidation is actually attracted more attention nowadays because indoor pollution is more when compared to the outdoor pollution. For this, immobilized TaO2 on glass and stainless steel, they are being used on porous substrate. They are being used, and they are able to eliminate the nitrogen oxides, carbon oxides, or volatile organic compounds, and also particulates. So it was reported the lanthanum doped TaO2 immobilized on high surface area of the porous ceramics exhibited excellent photocatalytic performance for acetone and nitric oxides. So here, this is the paper that is reported in that 2019 by using this lanthanum TaO2. And what are the reactions involved in the removal of the air pollutants? All of us know that any TaO2 or any semiconductor material, when it is excited, it forms superoxide radicals and as well as hydroxide radicals. So these hydroxide radicals can react with the nitric oxide, forming nitrogen dioxide or nitrate, or superoxide can react with the nitric oxide and nitrogen dioxide, forming the nitrates. So here you can see the initial reactions, and the reactions actually, these are the final reaction. That is, ROS is nothing but reactive oxidizing species. So they can oxidize this organic pollutant to the inorganic acid, or carbon monoxide to carbon dioxide, or nitrogen oxide to nitrites, likewise sulfur oxide to sulfuric acid. So I said that we prepared that silver bromide, hybrid paper, silver bromide TaO2. We found that it is able to degrade this, removes the ethanol in the gas phase under the visible light. And now know that hydrogen is a future fuel, and photocatalytic water splitting can be done by so many photocatalysts. Actually, here it is given a mix of rutile, anatase, and brucite. All the three phases of this TaO2, but they have the band gap more or less nearly same, but the band potentials are not same. So that is why you can see that potential conduction but potential of rutile is higher than that of anatase, which is higher than that of brucite. So once you irradiate it, electron transfer can take place. So when you have some this sacrificing agent like methanol, people can react with this methanol, producing that oxidizing product, and hydrogen, the electron can combine with each plus ion form hydrogen. So this is hydrogen production by this a mixture of three phases. Sometimes we can also use a mixture of two phases. And this is another catalyst where this cadmium sulfide, nickel phosphide, and this is also used for the production of photocatalytic hydrogen. Here, this sacrificing agent is lactic acid. So instead of, now they started using even glycerol also for the oxidation. So that we prepared some zinc oxide, europium oxide. In that zinc oxide, europium oxide, the hydrogen evolution is found to be nearly 15 ml, and compared to the zinc oxide, it's only 8.8 ml. And recently that we reported a catalyst that zinc indium sulfide, copper indium sulfide, and RGO. So it is, can see that hydrogen evolution in micromoles per hour, that zinc indium sulfide, RGO, copper indium sulfide is having the maximum evolution of hydrogen. And sometime back, I think you have seen a paper or even the newspaper cuttings that C.S. Gobinath, a senior scientist in CSIR, reported a catalyst that is nothing but an artificial leaf. You can see here, this is a Fukushima-Honda effect, whereas this is actually for desired observation. Here, if you have a photocatalyst, mix the photocatalyst in water and put it in the water, the hydrogen evolution is there. Similarly, this is actually a real example where in the slide he quoted the catalyst and put it in that water, and there is an evolution of hydrogen. You can see there is an evolution. Actually, this is not only a photograph. Otherwise, you can see that evolution of hydrogen here. So here, yes, this catalyst is a reported catalyst was gold TaO2, lead sulfide, and cadmium sulfide. So this catalyst that time he reported, he stated the device area of 23 square centimeter could produce about so much of hydrogen fuel per year. So Actually, this is the paper he reported in the scientific reports. And this is a very good research. And normally, if you have that facilities to measure the hydrogen and other things, and we can prepare the catalyst, and then this will be very useful because, as I told, that the hydrogen is going to be the future fuel for our vehicles and other things. And particularly, if you are able to get from the water, it's a very, very cheap. And now another one is the direct methanol fuel cells, and it's a future energy generation, particularly for electronics and vehicular applications. And here, earlier they used only platinum as the, catalyst, anode, whereas that it's susceptible for deactivation and poisoning. That is why they changed the platinum into another working electrode by using this nanomaterials. So we have not done any direct work on methanol fuel cells, but we tested our materials by using this cyclic voltammetry. So working electrode prepared by spraying the catalyst dispersed in the isopropyl alcohol on glassy carbon electrode, and we measured the current produced in the PV. So if you see that when you have zinc oxide, it gives only 1.5 milliampere. And whereas in the case of gadolinium zinc oxide, the current intensity is found to be 3.42 milliampere, and dysprosium zinc oxide is 4.64. So these are some of the current densities of the different catalysts. So when you have the higher current density, that means that catalyst is very suitable as a electrode for this methanol fuel cells. In case of dysprosium zinc oxide is suitable. Another one is called the photoconductivity study. Suppose if you expose that catalyst, you measure the dark current at different voltages, applied electric voltage. At the same time, you expose the catalyst with a 100-watt halogen lamp and record the photocurrent. So if the photocurrent is higher than the dark current, or if you have the positive photoconductivity, it says that the materials exhibiting positive photoconductivity is very useful for these solar cell applications. So one of the catalysts, that silver zinc oxide SnO2, as having a positive photoconductivity. Similarly, bismuth vanadium zinc oxide is also having a positive photoconductivity, photocurrent. So these are very useful, and we can test the photoconductivity of the nanomaterials and find the suitability of the material for these different applications, future applications. Another one is application of catalyst material in supercapacitor applications, and that is electroanode. Actually, here we measured this RGO holmium vanadium zinc oxide by CV. You can see the current densities, that wide current densities are that in curves are showing that. That means they have the higher capacitance performance. And similarly, this galvanic charge discharge time, when it is greater, you can see this is a holmium vanadium zinc oxide, whereas for different current, this one here, this is for RGO holmium vanadium zinc oxide. The charge discharge time is very higher, so this is very suitable for the supercapacitor applications. Typically, when you use a redox electrolyte, it becomes a charge discharge ratio time is also increases. So this is without redox electrolyte, and this is with redox electrolyte. That also can be used as a supercapacitor applications. So we have prepared actually this is one example of single atom photocatalyst. So you can see that single atom photocatalyst here, and they pprepared the TiO2 with palladium. So palladium 1 and copper 1 with incorporated in TiO2. And in another case, palladium 3-1, palladium 5-1, palladium 7-1, 9-1, and 11-1. So this one, they found that the palladium 7-1 loaded TiO2 is found to be very, very efficient in conversion of carbon dioxide to the methane. So this transformation was found to be very effective by using the single atom photocatalyst. So this shows the application of the single atom photocatalyst, or the efficiency of the application of this, efficiency of the single atom photocatalyst in the conversion of carbon dioxide to methane. So these are some of these energy applications of this photocatalyst. And earlier we have seen that environmental applications in the case of degradation of toxic chemicals, as well as this antibacterial activity and other things. Now, so this is why photocatalysis group, and all the students, I mean, maybe some of them are in Annamalai, some were in Kalasalingam University. So I thank the university and the Kalasalingam Academy of Research and Education for the facilities, and also this project MOEF and CR for funding. And this is actually, the mangrove forest near to Chidambaram. Chidambaram is a place where a university is located, not the name, is the name of the place. And here, this is the one which saved our people during the tsunami time. So it's a very good, one of the second largest mangrove forest in the world at Port Novo near Chidambaram. So one of the tourist spots. So thank you very much. This is our Lord Nataraja temple at Chidambaram. So thank you. This is Chidambaram. I told you that the temple city where Annamalai University is located. Thank you very much for your patience here. Thank you.
Thank you, sir, for your insightful presentation in which you clearly highlighted no materials, no progress, and also mentioned about different type of reactions and criteria one needs to pay attention to while working with nanocatalyst. Now we'll take a few questions from the audience.
I had one question to Professor Swaminathan.
Yes, sir.
This photocatalytic reduction of carbon dioxide to methane, right? Has this any application anywhere?
No, they tested actually, but we have not done that work anyway. But carbon dioxide actually now the progress, the carbon capture, that carbon dioxide conversion to methane is being done now. But practically, whether that come to the practice or not, I mean, I didn't have any idea about it.
Okay, because I was just wondering whether this technique can be used for reducing CO2 environmentally.
There is actually, when I went to UTP, University of Technology Petronas, Malaysia, they have a separate wing for conversion of carbon dioxide to methane, and they are doing the work. I don't know how, I mean, that catalyst, whether it is by photocatalyst or by some other, only photocatalyst.
Because even if you convert it into even if you convert it into methane, then methane, they must be using it somewhere. Further, it may be being used.
Yeah, we have to find some, because carbon dioxide conversion is carbon capture.
Yeah, no, environmentally, methane also cannot be released to the atmosphere because methane is also a greenhouse gas.
It can be used as a fuel. I mean, again, it's not a eco-friendly fuel, but it can be used as a fuel.
Methane has to be put into some other use. Because CO2
earlier there was a report on methyl alcohol, conversion of methyl alcohol, it was there earlier.
I mean, from the greenhouse point of view, conversion of CO2 to methane will not solve the problem because methane is equally dangerous in global warming. But they might put that into further use. So that's a different thing.
Yeah, other uses, yes.
Yeah.
Another thing is that that now water splitting is one of the growing area. Everybody started doing that one.
Yeah,
because,
it's very interesting. I saw your slide on artificial leaf. What do you call this artificial leaf?
No. In just like photosynthesis, you are converting carbon dioxide and water into the starch.
Yeah, splitting
like
water.
That, water. Yeah,
photosynthesis.
Here the water is being converted into hydrogen. I mean, that is the thing. Now the thing is that solar energy is consumed just like your leaf. See, consumption of solar energy gives rise to that hydrogen fuel. So that is why he has he has mentioned it. He has mentioned it as artificial artificial leaf. That is why he mentioned it as an artificial leaf.
Yeah, this is for the hydrogen, producing hydrogen as a fuel from water, right?
Yeah. Splitting of hydrogen into water into hydrogen. That is it.
Okay, thank you.
Sir, I have also one question. Sir, thank you for very informative session. Sir, I want to ask, sir, as you show the HRTM images of nanoparticles, so in that images, one images is of lattice fringes. So, sir, may
Huh?
I know this very basic question, sir? Sir, may I know what is the actual application of what kind of information we get from that lattice fringes in HRTM images?
No, lattice fringes, we found that the presence of some material. For silver TiO2 is there means you have the lattice fringe, I mean, that is equivalent to silver and as well as for the TiO2. So based on the linings, that lining gap, that
Yes,
from the gap you can find out the presence of these materials. And the Sayed pattern, when you have the concentric rings, you can find whether it is a crystallinity of the material. Okay, in the HRTM images, these two are used only to find the crystallinity of the material and as well as the presence of the different type of silver or zirconium oxide or this TiO2, whether they are really present or not.
Okay, sir. So we can calculate the gap, the length of the gap between
Yeah,
two
that is
lines.
possible to calculate the gap. Sometimes 3 or 4 materials, it is very useful. You can find the different gaps in that one.
Okay. Thank you, sir.
Thank you, sir. Moving on, as our second speaker, we have with us Dr. Naveen Chandra G. Shimpi. Dr.
Thank you
Naveen
very much
Chandra
for the
Gopal
opportunity
Shimpi.
given to me. Thank you, sir.
Thank you, sir. Dr. Naveen Chandra Gopal Shimpi is a distinguished professor in the Department of Chemistry at the University of Mumbai since April 2014, with an academic journey spanning notable achievements. He earned his PhD from North Maharashtra University in 2006 and since then has made significant contributions to the field of chemistry. Dr. Shimpi's outstanding research endeavors have secured substantial funding from prestigious agencies such as UGC, DRDO, CSIR, DST, AICTE, and MHRD TEQIP, amounting to approximately 2 crores. His academic prowess is completed by a plethora of accolades, including the Young Scientist Award from the Asian Polymer Association, Dhyan Jyoti Puruskar from Shirsate Foundation, Jalgaon, SF Elsewhere International Best Researcher Award, ACT's PG Best Teacher Award, and the Best Teacher Award from the University of Mumbai. Dr. Shimpi has an extensive publication record with over 100 papers in high-impact international journals, and he has also delivered over 100 invited lectures. Furthermore, Dr. Shimpi has supervised numerous students, with 15 successfully completed their PhD under their guidance, while 8 are currently pursuing their doctoral studies. He holds 2 granted patents and 4 pending patents, and he has also undertaken consultancy projects for notable organizations. Beyond research and training, Dr. Shimpi has organized several national and international conferences, staff development programs, and professional certification courses. He is actively involved in editorial roles, serving as an associate professor for the International Journal of Chemical Studies and a review editor for Frontiers in Chemistry. He has also acted as the lead guest editor for a special issue of the International Journal of Polymer Science. His scholarly contributions are evident in his impressive citation count of 2,800 and a distinguished H index of 32. Additionally, he is a member of the Executive Council of the Asian Polymer Association, a fellow of the Maharashtra Academy of Science, and a life member of the Indian Science Congress, all of which highlight his significant impact on the scientific community. Recently, he has edited books on biodegradable and biocompatible polymer composites, as well as carbon-based nanomaterials and nanocomposites for gas generation sensors, further solidifying his reputation as a leading figure in the field of chemistry and material sciences. Having you here with us, sir, is a genuine privilege. I humbly request you to share your wisdom and address the audience with your kind words. Over to you, sir, please.
Slides are visible to all of you properly.
Yes, sir, your slides are visible.
And am I audible clearly?
Yes, sir.
Okay, thank you. For purposefully, I just mute my video for proper bandwidth. Good afternoon to all of you. And before to start with my lecture, I thanks to the organizers for inviting me to deliver my expertise in the field of nanomaterials and nanotechnology in Ankur 2023. I thanks to the Vice Chancellor of the University, Director, Dean, Faculty of Science and Technology, Dr. Kavita Sharma, my good friend, Dr. Gurnale, ACT Secretary, General Secretary, Professor D.V. Prabhu, and other colleagues who are continuously working for the grand success of this event. And also dear students who are joining to the backside of the stage. Today, I will talk on PAN nanofibers supported silver graphitic carbon nitride and copper nickel carbon nanofiber composites, its property investigation on photocatalytic and supercapacitive properties. This is the content of my presentation. General introduction with PAN zinc oxide hybrid nanofiber, their synthesis, thermal and mechanical properties, photocatalytic activity, its mechanism. PAN AGG hybrid nanofibers, same, that is synthesis and characterization, thermal and mechanical properties, photocatalytic activity, mechanism. PAN AGG C3 and 4 hybrid nanofibers, copper nickel carbon nanofibers, and summary and future scope of the work. Initially, when we talk about the field, that is a nanotechnology, that we know that nano is nothing but a very small particle. Everyone is saying the small particle, or we say 1 nanometer equals to 10 to the power minus 9 meter. But when we talk about the nanotechnology, the word itself suggesting very small. But when we have the actual definition, that is at least one dimension should be in the range of 1 to 100 nanometers, then the material is said to be as a nanomaterial. These are the scale benchmark from where we can understand about the nanomaterials. And there are the dimensions, that is 0 dimension, high specific surface area. When we talk about the 1-dimensional light scattering and non-worn material, when we talk 2-dimensional material, they are smooth surface with high adhesion power. When 3-dimensional have high carrier mobility. Means considering the dimension-wise activity, the properties and activity of the material is going to be changed very drastically. And when we talk about this nanomaterial, surface to the volume ratio is one aspect, but at the same time, morphology is also playing one of the important aspects during the application, as well as the change in the properties from micron size to the nano size. When we talk about these nanomaterial, there are the 2 aspects of nanomaterials. First is the that is the molecular size conversion and atomic size conversion. Atomic size conversion means conversion of metal to the nanometals. And when we talk about the molecular size conversion, that is a material is converted into bulk material is converted into the nano size that comes into the molecular level. And when we talk about the aspects, there are the 2 approaches. One is a top-down approach, and second one is a bottom-up approach. Mostly, we have a very good trust on the bottom-up approach because the size control is very precise. Means we can easily manipulate the size by changing the parameters of the reaction, that is a concentration of the solution, then pH of the solution, then pressure, temperature of the reaction, then by changing the various aspects which are associated with the chemical reaction. Upon changing this parameter, we can easily control the particle size of the nanomaterial. 1-dimensional nanofibers, when we talk about the 1 dimension, as I mentioned in my previous slide, 0 dimension, 1, 2, and 3 dimension, in that 1-dimension nanofibers we are talking. Why 1-dimension nanofibers? Before to go with why 1-dimension nanofiber, to the right side, there are the application of electrospun nanofibers. These material can be used as for the purpose of the filtration, and that is air filtration, ion exchange membrane, as an ion exchange membrane. For the energy to storage application, that is specifically for the batteries, supercapacitor, and in solar cell. Textile, when we talk about the textile industry, smart clothing, then protective clothing and fire retardant fabrics. Catalysis, that is that material can be used as a photocatalyst. That material can be used in the organic transformation reaction. When we talk about the sensors, these material can be used in the flame resistive sensor, that is chemical sensor, piezoelectric sensors, and in biomedical application, because of the these application, these specific properties of the material, they have the good advantage in the biomedical application for the purpose of the drug delivery, then tissue engineering, and in wound dressing. So why these applications are specifically been defined? The large specific surface area. Material is a very advanced, high porosity. Porosity is one of the most important aspects for the nanofibers. When we talk about the porosity, high porosity, in connection with the high porosity, whatever the single pore size is there, that single pore size should be very smaller one. Robustness, easy reusability, having high thermal stability, as well as it's having a high mechanical strength. When we talk about the high thermal stability and high mechanical strength, when we go with the filtration, that is as an ion exchange membrane, it needs a very good mechanical strength. If the strength is very less, then material cannot be sustained for a long filtration purposes. When we talk about the sensor, if there will be some heat going on during the sensing application, then thermal stability of the material should be very high. If thermal stability is very high, then material can be used as a very base sensor. Methods for fabrication of nanofibers. There are various methods for the fabrication of the nanomaterials, nanofibers. But when we talk about the fabrication of these nanofibers, here electrospinning technique is being used specifically because laboratory based material technique, potential for industrial processing, repeatability can possible because we can change the parameters continuously, and upon changing the parameters we can develop the nanofiber as per our requirement. Therefore repeatability can possible. Moderately easy when we talk about the processing way for this particular technique, that is the electrospinning technique. That technique is a very easier one, moderately very easy. Only why we say moderately, because here we are using the high voltage parameter is very one important aspect, and we have to taken care of that during the processing. The high voltage should not be seed out of the box. Then advantages, simple process, very cost effective, large variety of polymers can be electrospun, near about natural polymers. When we talk about the natural, more than 30 natural polymer can be utilized for the fabrication of these nanofibers with the doping of metal and metal oxide over the surface of or decoration we talk it. Then can be production of aligned nanofiber is also feasible. Complex, these are the advantages of this limitation. When we talk about the limitation, the voltage is one of the control size, the control way to have a very control over the processing condition, so that it's that voltage should not be seed towards the box of that electrospinning setup. This is the electrospinning unit. Here we have shown that electrospinning unit. When we talk about the electrospinning, what is the condition? A high voltage power supply is needed. Normally, the range is 10 to 30 kilovolt. When high voltage is applied, we are applying the high voltage. This is the needle, and this is the crocodile pin through which we are applying the voltage to the needle. The voltage is being applied to the needle, and when we apply the voltage to the needle, liquid becomes charged. Whatever the liquid comes from the syringe, that liquid is getting charged, and upon charge, the liquid comes out from the syringe. That charged liquid comes from the syringe, and electrostatic repulsion counters the surface tension, and the droplet is stretched. Whatever the droplet comes from this particular point, that this is the point from where the droplet comes, it gets charged, and stretch, at a critical point, liquid get erupts from the surface. If the molecular cohesion of the liquid is high, stream breakup does not occur and charged liquid jet is formed. A conductive substrate is there. Here is the substrate, where this is the drum. We call it as a substrate, where the fibers are get collected and roll over the surface, normally grounded, which serve as a collector for the electrospun fiber. A conductive substrate is there. Vertical or horizontal view. There are the two ways of drawing the fiber. One is by the vertical means and another is by the horizontal means. These are the methodologies. Synthesis, we are synthesizing the material, we are characterizing the materials, then we have the applications, then reaction, we think over the reaction parameters. First, we talk about the fabrication of PAN nanofibers. Step 1, 10% of PAN solution was prepared by dissolving it into dimethyl formamide at 60 degrees centigrade for 3 hours and stir overnight at room temperature to obtain homogeneous solution. Initially, you have to prepare the solutions. And once you prepare the solution, you can measure the viscosity, because when we talk about the electrospinning technique, there are the different parameters which needs to be taught. That is the processing conditions are very important for this particular material. And therefore, a moderate viscosity solution of polyacrylonitrile is required. The prepared solution was electrospun with a flow rate. That is, this is the flow rate, means whatever the searing is there, to that particular searing, once we fill the searing with the help of by using this PAN nanofiber PAN solution, polyacrylonitrile solution of 10 weight %, and once we push the solution from the needle, whatever be the flow rate is there, that should be 1 ml per hour. 1 ml should be per hour. 1 ml of the solution should pass per hour with the voltage, whatever the voltage we are applying, and that is a 20 kilovolt we are applying with tip collector. Distance between the needle and the distance between the collector plate, that is that should not be exceed 20 centimeter. Okay. Finally, fibers were collected on a collector plate and dried. Hello, am I audible? Hello?
You are audible.
Yes. So, as I mentioned, effect of the parameters on drawing of the fibers, effect of concentration. Effect of concentration means what? The viscosity of the solution is very important. When we talk about the concentration effect, see, 10 weight % of the solution gives this much of the fiber. 12 weight % of the solution gives this much of the fiber. 15 weight % of the solution gives this much of the fiber. When a solution viscosity is 10 weight %, the fiber size and the diameter is ranging between 200 to 400 nanometer. But if we increase by 2 weight %, means if we move to 12 weight %, the size goes on 700 to 800 nanometer. And again, if we go by increasing the viscosity by 5 weight %, means 15 weight %, it goes to the micron size. Means a moderate viscosity is the base, means 10 weight % is the base viscosity, that is the concentration for drawing the fiber in between 200 to 400 nanometer. Effect of applied voltage. As I mentioned, voltage should be setup, whatever the setup we have, electrospinning setup, the capacity of that electrospinning setup is having the voltage of 10 kilovolt to 30 kilovolt. And when we talk about the voltage, if we increase the voltage from 15 kilovolt, if we apply 15 kilovolt, then it gives 344 plus or minus 51 nanometers fiber diameter and size. If we go with 20 kilovolt, it gives 323 plus or minus 22 nanometer. And if we go 25 kilovolt, it gives 331 nanometer. Means if we look into this, 20 kilovolt is the appropriate voltage condition which we have to apply to the needle so that the fiber size should be in the range of 323 plus or minus 22 nanometer. If we talk about the distance between the tip and the collector plate, the distance, if we keep distance 15 centimeter, then it gives 438 nanometer size. And if we go with 20 centimeter, it gives 368 nanometer size. Means every parameters we have to look into it so that we have a very good quality of the fibers in our hand. That is the first is the concentration of the solution. Second is the applied voltage, and third one is the tip to collector distance. Now fabrication. I have simply mentioned the formation of fabrication of PAN nanofibers only. Now this is the combination, that is a hybrid nanofiber. Such type of the fibers are when we have any metal or metal oxide over the surface of the PAN nanofibers, such a fibers are called as a hybrid nanofibers. And this type of the fiber is PAN zinc oxide hybrid nanofiber. Initially we synthesize zinc oxide nanorods. This is the method we have shown here, the synthesis of zinc oxide nanorod. Co-precipitation technique was used. Sodium dodecyl sulfate as a surfactant being used. And NaOH, by changing the concentration of the NaOH, we can maintain the pH, we can maintain the concentration, we can have the proper aging time. And after following the process of co-precipitation by applying the proper condition of concentration of the solution, pH of the solution, temperature of the reaction, then we can have a final material, that is a zinc oxide nanorods. That is the C-axis growth is taking place. When we go for the calcination, the C-axis growth is taking place for the conversion of zinc oxide to the nanorods. Morphology to the nanorods gives the C-axis growth. After synthesizing this, already we have the PAN solution in our hand, 10% of the PAN solution. To that solution, we are adding zinc oxide nanorods, and the entire solution was stirred properly under ultrasonic cavitation technique for the uniformity purpose. And then keeping the solution in the syringe, once we apply the pressure, the solution get pushed to towards the needle, and it drawn into the fibers form. And dry this particular material at 80 degrees centigrade, and we have in our hand, that is a PAN zinc oxide hybrid nanofibers. Fabrication of PAN silver graphite hybrid nanofibers. We have graphite in our hand, that is by applying Hummers method, we convert this graphite into graphene oxide. Okay, then in situ process we have applied, we prepare the solution of silver nitrate, we add this solution in silver nitrate into the graphene oxide. Once the solution been added dropwise, we allow the solution, entire solution, for the sonication for 1 hour by 5 seconds on and off condition. Once the process completed, we have such type of the structure. We add sodium borohydrate as a reducing agent. By adding the sodium borohydrate as a reducing agent at 95 degrees centigrade, we get silver graphite hybrid nanofibers. Okay, silver graphite is formed, and after the formation of this silver graphite solution, we can add this into the PAN, that is a polyacrylonitrile solution. We stir this solution or put the entire solution in the ultrasonication process for uniformity or for uniform dispersion, then transfer to the electrospinning technique. We have PAN AGG hybrid nanofibers. Further, we synthesize PAN silver graphitic carbon nitride hybrid nanofibers. This is the way of the synthesis of graphitic carbon nitride. We have the urea pyrolyzed at 550 degrees centigrade. We get graphitic carbon nitride, that is a GC3N4, and the bulk graphitic carbon nitride solution put under sonication in presence of in presence of silver nanoparticle. We make the solution, entire solution, and prepare silver graphitic carbon nitride nanoparticles. Then further we transfer the solution to PAN, that is a 10% solution of polyacrylonitrile, and the entire solution is being transferred for the electrospinning technique, and we get PAN AGG C3N4 hybrid nanofibers. This is the fabrication of copper nickel carbon nanofibers. We have synthesized these. We have used copper nitrate, nickel nitrate. Then we transfer the entire solution, that is a in situ technique we have used. After in situ technique, with whatever the copper nickel nanofibers we have, copper nickel nanoparticles, that copper nickel nanoparticles been transferred into the polyacrylonitrile solution. and we draw the fibers of copper nickel carbon nanofiber. This is the way carbonization process we have followed. After carbonization, complete carbonization, that nanofibers are converted into the carbon nanofibers. These are the characterization for techniques for pan zinc oxide, and zinc oxide. The combination of the peak from pan and zinc oxide suggesting the formation of pan zinc oxide nanofibers. This is the FAR IR study. In this FAR IR study, if we look into this FAR IR region, that is a presence of peak that is a 891 centimeter inverse to 718 centimeter inverse, suggesting the formation of zinc oxide bond that forms the zinc oxide nanorods. Then pan is nothing but the acrylonitrile group is there. Presence of the acrylonitrile group is suggesting here that is a formation of the pan. And then after the complete process of electrospinning followed, we done the FTIR for pan zinc oxide. Presence of zinc oxide peak with combination of pan functional groups suggesting the formation of pan zinc oxide nanofibers. This is the XPS study, that is a convoluted and deconvoluted spectrum from 01S, C1S, C1S, Zn2P half, Zn2P 3/2. This is nothing but the formation of the zinc with combination of oxygen, and presence of the carbon is suggesting the pan here itself. Okay, so this is the X-ray photoluminescence spectroscopy we had done to study the binding energy for the synthesized zinc oxide, pan, and pan zinc oxide nanofibers. These are the deconvoluted spectrum, zinc oxide nanorods showing the two ways, that is a Zn2P 1021.36 electron volt to 10444.6 electron volt. Same for the pan, only single peak is being observed here. And when we talk about the pan zinc oxide nanofiber, the merging of the peak is being observed. And these are the Rosette structure of hexagonal Zn2 plus ion array. Oxide ions in the crystal lattice with Zn2P 3/2 species in zinc oxide, Zn2P half in that crystal lattice along the C-axis growth, and the presence of the cyano group is from the polyacrylonitrile. This is the UV dye study. We have the zinc oxide, whatever the binding, if we look into this 3.440 electron volt for the zinc oxide, but when we have pan zinc oxide nanofiber, it has 2.10 electron volt. This is the FASM study. Zinc oxide nanorods are clearly been observed, and the decoration of the zinc oxide nanorods over the surface of the pan is being observed. This is the TAME and EDAX study, presence of the, that is the elemental study, carbon, nitrogen, oxygen, and zinc. This is the percentage distribution of the presence of pan in zinc oxide or decoration of the zinc oxide over the surface of the pan. If we look into the image C here, the complete patch been observed, that is a rod is being placed over the surface of the nanofiber. This rod dark zinc oxide, and this other surface, remaining surface is nothing but the nanofiber. We have done the BET. If we look into the average pore size, zinc oxide is showing 3.63 nanometer. Average size of pan is 2.2 nanometer, and average pore size of pan zinc oxide is 2.9 nanometer. Thermal stability, thermally more stable, that is a pan zinc oxide nanofibers. If we look into the pan, melting temperature of pan is 307 degrees centigrade, while because of the addition of zinc oxide, pan, the melting point is goes on increasing, that is a 350 degrees centigrade. Mechanical properties, tensile strain, elongation at break, Young's modulus, and hardness of this particular material is found to be increased with increasing the weight percent loading of zinc oxide nanorods. We study the visible light photocatalytic activity of this material. Photocatalyst, we know all about the photocatalyst, is a substance that uses the light energy to facilitate the chemical reaction. This is the general way of photocatalytic activity. There are the two forms. One is the oxidation and second one is the reduction. This is the degradation product of during the reduction process, and this is the degradation product during the oxidation process. Okay, So copper sulfate photocatalysis is being used because of the there is a simultaneous formation of the electrons and the holes, creation of the holes and formation. This change in the band gap itself increasing the photocatalytic activity of this material. Chlorophyll is the natural photocatalyst, as you all know. These are the application of the photocatalyst: sterilizing effect, deodorizing effect, air purifying effect, anti-fogging and self-cleaning, water purification and dye degradation. This is the general way. That is a carbon dioxide plus water. When goes photosynthesis, it forms the glucose and the oxygen. Why we have to think about the photocatalyst for the purification of the water or for the degradation of the dye? 2 billion people belonging to 60 countries of the world are dying because of the lack of the water. And if we move ahead, that is up to 2050, the figure may go up to 7 billion. Initially, this is the way of getting the water. The crow is searching for the water. He drops the stone inside the pot. The water gets lifted by the weight of that particular stones, and he takes the water. But if the amount of the water is less, that time what he has to do? He uses the straw for picking the water. But again, the amount of water goes on decreasing. This straw is again useless. Then he will use this motor to lift the water, but the pot is empty. What does this motor will do? So we have to think. For the last 3 generations, our family was very scientific in managing the water problem. But what can I do when there is no water in the lab? If water is not there, then we have to search for the options. Whatever the water is left, maybe the impure or whatever the salty water is there, we have to think about the filter to filter that water properly with the help of this material as a photocatalyst. This is the scenario right now. For this, we have done the photocatalytic activity of malachite green. Initially, when we have done we have used these 2 dye, malachite green and methyl orange. This is the pan nanofiber. Only in presence of the pan nanofiber, the degradation seems to be very negligible, very negligible. In case of the zinc oxide, the degradation is taking place at in 180 minutes. That is 89.0%. But in presence of pan, it is 24.8% degradation of malachite green is been observed. But when the combination, that is a decoration of zinc oxide over the surface of the pan, gives a very interesting degradation, that is 96.3% degradation of the malachite green been observed. At 200 minutes, the complete means nearby 100% degradation being observed, that is 96.3% degradation. When we talk about the methyl orange, in case of the methyl orange, pan singly unit shows 21% degradation. In case of the zinc oxide nano rods, 74% degradation. But pan zinc oxide nanofiber, hybrid nanofiber showing 90.3% degradation. And when we compare with malachite green and methyl orange, it has been observed that malachite green pan zinc oxide nanofiber is very much selective for the malachite green because it gives 96.3% degradation rather to 90.3 as in case of methyl orange. Without catalyst, no degradation. This is the malachite green, this is the methyl orange. 0 minute to 280 minutes we have done, 0 to 200 minutes. The degradation is not been observed. We have done the kinetic study. It is a that study, Ng and MO dyes degradation follows the pseudo unimolecular first order kinetic reaction. Then pan zinc oxide nanofiber. When we look into the pan zinc oxide nanofiber, the surface of this electrostatic stabilization. When we talk of the surface of malachite green, cationic dye positively charged, and when we talk of methyl orange, anionic dye negatively charged. So negative surface because of the negative surface from the pan zinc oxide nanofiber and negative surface from the methyl orange surface. shows the slower degradation. But positive surface from melted green and negative surface from this shows the effective degradation, that is a faster degradation. Okay, interaction between the dye molecule and the photocatalysis is taking place properly, and melted green respond very effectively as compared to methyl orange. After doing this particular study, we have done the zeta potential, and zeta potential is showing a very negative, means below it nearby, I think 25 millivolt, that much of the zeta potential being observed for that particular material, the pan zinc oxide nanofiber. This is the mechanism. As everyone knows about this mechanism, we have done the study in presence of the quenchers. So these are the different quenchers, no quencher, then isopropanol, then benzoquinone, and the sodium EDTA we have used here. Okay, and by changing the quenchers, in case of the melted green and methyl orange showing 97% degradation. Melted green shows 97% degradation in absence of quencher, while it shows less than 97%. Means again here, if we look into this, the pan zinc oxide nanofiber is very selective for melted green dye. This is the reusability study we have done. We have studied the reusability study up to 5th cycle. Very impressive results we find here. That is a marginal decrease in the degradation of melted green is being observed up to even 5th cycle. So this is the reusability study. After reusability study, we have done the same. If we look into the same, that nanofiber does not lose, pan zinc oxide nanofiber does not lose its activity. Porosity is same, but somewhere marginally decrease in the porosity, and because of the marginal decrease in the porosity, after 5th cycle, there is the rate of the degradation seems to be lesser as compared to the 1st, 2nd, and 3rd cycle. We have done the FTIR also. There is no change in the peaks, and this is the comparative study. Pan zinc oxide nanofiber melted green takes degradation within 200 minutes. Pan zinc oxide nanofiber methyl orange in 280 minutes. These are the characterization of next material, that is a pan AGG hybrid nanofiber. XRD and FTIR. As I mentioned, this is the silver graphite nanoparticles. This is for the pan. And when we decorate this AG silver graphite over the surface of the pan, the combination of both pan and AGG nanoparticles been observed in case of the pan AGG hybrid nanofibers. The same is being observed in case of the FTIR. This is the XPS and FASM study we have done. That is a silver graphite nanoparticles showing the petals like it is a flex-like structure. Pan nanofibers are rod shaped material, and the decoration is being observed in case of the pan AGG hybrid nanofibers. This is the convoluted and deconvoluted spectra of pan AGG hybrid nanofibers. This is the binding energy study with the help of the XPS. This is the TAME. Here is the dark spatch, is nothing but the silver graphitic nanomaterials over the surface of the pan. Thermal properties, thermally more stable. The hybrid material is thermally more stable as compared to the pan and as compared to the AGG nanoparticles. When we talk of the pan, 288 degrees centigrade might be due to some instrumental effect. The temperature 288 degrees centigrade is the melting point, and when we add silver graphitic nanoparticles over the surface of pan, the melting temperature goes to 316 degrees centigrade. These are the mechanical properties. Tensile strain, elongation and break, Young's modulus, and hardness seems to be increased. Now, solar irradiation study as a photocatalyst. Here we use methylene blue and methyl orange. If we look into this pan, 25%, silver graphite nanoparticles show 79% degradation, whereas pan AGG hybrid nanofiber gives 88.1% degradation for methylene blue. And for methyl orange, 24%, 74%, and 82%. Again, when we compare between methylene blue and methyl orange, the rate of degradation is faster in case of methylene blue as compared to methyl orange. This is the without catalyst, that is a blank titration. Kinetic study of MB and molecular methylene blue and methyl orange suggesting the pseudo unimolecular first order kinetic reaction. This is the degradation mechanism. Okay, because of the change in the band gap, the degradation is very effective in both cases, that is the methyl orange as well as methylene blue. This is the reusability study. We have again used this material up to we go with up to 5th cycle, and methylene blue shows 91% even up to 5th cycle, and methyl orange shows 84% degradation up to 4th cycle. These are the types of the quenchers we have used for methylene blue and methyl orange. We have done the TOC removal content for this material. PAN AGG hybrid nanofiber shows 86% TOC removal, whereas methyl orange shows 80%. This is the reusability study. We have done the reusability study up to 5th cycle, and we have done the XRD, FASM, and FTR study for the 5th cycle recovered material. Here, if you look into this, the porosities still remain as such, but somewhere the porosity, porous structure of the material is get blocked due to continuous use of this particular nanomaterial, nanofiber as a catalyst, as a photocatalyst for the degradation in presence of the solar irradiation. This is the comparative study. PAN AGG nanofibers for methylene blue in 75 minutes shows effective degradation, while methyl orange takes 90 minutes for the degradation of the solar light, that is up to 88 to 91% in case of the methylene blue, and it is nearby 86% for the methyl orange. Next is PAN AGG C3 hybrid nanofibers. These are the XRD and FTR study. This is the thermal stability and FASM study of this material. PAN AGG C3 and 4 hybrid nanofibers is thermally more stable as compared to the PAN and AGG C3 and 4 nanoparticles. If we look into AGG C3 and 4, it looks like some gelatinous structure is been observed, and PAN nanofiber very somewhere uniformity, somewhere fineness in the diameter. And if we look into this structure, this is like a bone structure is being observed because of the effect of the processing condition. This is the same EDS mapping of PAN AGG C3 and 4 nanofibers. This is the XPS study that PAN AGG C3 shows the presence of oxygen 1s, nitrogen 1s, silver 3D, that suggesting the combination and decoration of AGG C3 and 4 over the PAN nanofibers. This is the deconvoluted spectra, AG 3D 3x2, AG 3D 5x2. This is the TAME. A beautiful decoration is observed of silver graphite carbon nitride nanofibers over the surface. And this is the elemental mapping, elemental study. The presence of silver, carbon, nitrogen, and nitride group is being observed clearly. This is the percentage of this particular material. We have done this heterogeneous catalyst for visible light driven for the selective oxide. This is oxidation of styrene, CH2 bonded molecule, and benzene. Initially, we go with the styrene oxidation. This is the styrene, simple light being used and the catalyst is nothing but the PAN AGG C3 and 4 nanofibers and H2O2 as the oxidizing agent, H2O2 hydrogen peroxide. And there is a formation of these products 1, 2, 3, and 4. The product in the square, that is the presence of this one. Initially, the conversion of styrene to styrene oxide, then benzaldehyde, then benzoic acid, and phenylacetaldehyde. See, this is the styrene oxide. This is the your benzaldehyde, then benzoic acid, and a formation of the phenolic group is there. Okay. So if we look into this, pan C3 and 4, we have used different catalysts. Silver nitrate, graphitic carbon nitrate, without catalyst, silver graphitic carbon nitrate, and the combination of this hybrid nanofiber. We have used the solvent, here CH3CN being used as a solvent. And if we look into the reaction time, 16 hours are required. But when we talk about the conversion, overall conversion of this product is 98%. But if we go with the selectivity study, styrene oxide shows 60%, benzaldehyde is showing 32%. For then this phenylacetaldehyde is 7%, and benzoic acid conversion is just 1%. Means overall conversion is 98%, but this particular catalyst is very much selective for styrene oxide. That is 60% of the styrene oxide can be possibly to get from this particular reaction. Catalyst screening and reaction optimization. We have done this screening. We have changed the alkyl group here. pH, 4CH, 4Br, 4Cl, 4NO2. Conversion 98% for phenyl, 98% for methyl. But when we talk about the styrene oxide, 65% been possible for in case of the alkyl group, that is a CH3 group. Okay, means it is very much selective for the CH3 alkyl group. CH oxidation of ethyl benzene. Here again, the same condition we have used. Time required for the reaction is 12 hours. This is the red color entry. That is a 12 hours required. Conversion is 98%, and complete formation 99% of this material, that is ethyl benzene, can be possible. That is a acetophenone. Conversion of this material into acetophenone is 99%. Overall 98%. These are the different derivatives. We have reactants. These are the reactants we have used. These are the different products we have obtained. Conversion and the selectivity. CH oxidation of benzene, 30 minutes reaction, 99% conversion. Benzene to phenol, complete conversion, 99%. This is the scalability, 3 millimole of the reaction being taken place. 86% conversion is being observed. Gram scale reaction was conducted using 0.228 gram of benzene. The scale-up reaction affordable the phenol with 86% in 30 minutes. This is the reusability study we have done, pan, ADG, C3 and 4 nanoparticles. That is we have done this run this reaction up to 8 cycle. And when we look into ICP AES study, silver concentration before reaction was 4.56%. But even after 8 cycle, the silver concentration over the surface of pan in presence of graphitic carbon nitrate as a nanoparticle, it is 4.55%. Means silver concentration is still remain even after 8 cycle. Means we can go more than 8 cycle, but the percent yield of the product might be reduced. Copper nickel carbon nanofibers. Ratio is being used 2:1, 1:2, 1:1. Copper oxide carbon nanofiber, nickel oxide carbon nanofiber. These are the XRD study. This is the XPS. Carbon nanofibers, copper oxide carbon nanofibers, nickel oxide carbon nanofiber, copper nickel carbon nanofibers with 1:1%. Copper nickel carbon nanofiber with 1:2% and 2:1%. This is the deconvoluted spectra. This is the thermal stability. Majorly all materials are thermally more stable because of the combination of the copper nickel carbon nanofibers. This is the FeSM and EDAX-free carbon nanofibers, copper oxide carbon nanofibers, nickel oxide carbon nanofibers, and copper nickel carbon nanofiber of 1:1%. We have taken select the 1:1%, and this is the EDAX. These are presence of the elements in the material. This is the high resolution transmission electron microscopy, the decoration of copper and nickel over the surface of the carbon nanofibers. And this spectra is suggesting the polycrystalline nature of the material. We have done the cyclic voltammetry. If we look into copper nickel carbon nanofiber of 1:1 shows the scan rate 5 millivolt per second inverse is gives more current density for carbon nickel carbon nanofiber at 1:1% as compared to 1:2, 2:1 as compared to nickel carbon nanofiber, copper nickel nanofibers, and carbon nanofibers itself. We have done this study with reference to potential and with current density. The scan rate we have done 5 millivolt to 200 millivolt per second. That blue line of copper nickel carbon nano seems to be very rich in current density. The cyclic voltammetry of copper nickel carbon nanofiber 1:1 with varying scan rate from 5 to 200 millivolt per second. We have done the charge discharge study. 1:2 is getting discharged very fast. When we talk about this carbon nickel carbon nanofiber 1:1, this is charging very fast, but discharging is very less. Carbon nickel nanofiber with varying current density from ranging from 1 to 50 A per gram. This is the cycling stability and Nyquist plot. Here is the values of this particular 0.244 seems to be very effective for this 1:1 carbon nickel carbon nanofiber. This is the conclusion of the study. Electrospinning technique seems to be very effective for drawing the hybrid nanofibers. That is, I say here hybrid because the decoration is very easily possible. The pan surface, over the pan surface, the decoration of the zinc oxide, decoration of silver graphitic carbon nitride, decoration of silver graphite nanoparticles, and they are uniformly distributed over the surface because of maintaining the condition, by maintaining the processing condition of the electrospinning technique. When we done this, the hybrid nanofiber possesses high specific area, that is 98.05 meters square per gram, along with structural flexibility, good structural flexibility, good thermal stability, good mechanical property. And considering this, they are very good photocatalysts for the degradation of the hazardous dyes, for the as a photocatalyst for the organic reactions. That is, we have done conversion of styrene to styrene oxide, benzene, and CH2 molecule, and they are mostly methylene, malachite green, and methylene blue. Seems to be very selective for that particular selective selective catalyst. Copper nickel carbon nanofibers is a ratio ware fabricated using electrospinning technique, followed by structural elucidation using different techniques. XID analysis reveals impregnation of copper oxide, nickel oxide into carbon nanofibers, and thermal stability shows the material are thermally more stable when we dope that material over the surface of the pan or convert into the carbon nanofibers. These are the future scope of the study. Various polymeric nanofibers such as polyvinyl alcohol, polyethylene oxide, polycaprolactam can be studied for the applications such as drug delivery, tissue engineering. Different hybrid nanofibers with inorganic materials such as semiconducting metal oxide can be fabricated for advanced properties. Then various conducting polymer like polyacrylone, polyaniline, polypyrrole, polythiophene can be used for the gas sensing capabilities and energy storage devices. Then different nanoparticles such as gold, palladium, platinum can be used for the vast application. Mostly we can again look into the matter that surface of pan or nanofiber, over the surface of the pan nanofiber, we can decorate metal organic framework also. As the metal organic framework is nothing but the combination of the metal or the organic inside the organic framework, that is organic linker is there. And because of the frame, it has the good porosity, and the surface of that particular pan nanofiber is having the good porosity. And if we combine these, definitely a beautiful structure can be obtained. And these material can be used for various applications, for the biomedical application, for the degradation of the dyes, for the organic transformation reaction, for gas sensing application, and as well as this material can be used for the specialized application for the defense research and development organization, that is for the defense purpose. This material can be used a very high specialty advanced nanomaterial for the increase in the thermal stability of the material. Flexible material, they can be used for the shape memorable polymers also. This is the research group. This is previously from my Jalgaon University. Thank you. This is the mechanism for the oxidation of ethyl benzene for the formation of acetyl or the how this reaction can be proceed. This is for the phenol conversion, benzene for the phenol conversion. Thank you. Hello.
Thank you, sir, for the enlightening presentation, in which you have also mentioned future scope of nanomaterials in vivid areas, specifically in defense. Now the floor is open for question and discussions. Okay, moving on. As our third speaker, we have with us Dr. Vasudev B. Gurnule. Dr. Vasudev B. Gurnule is an accomplished chemist with a distinguished academic and research career. He earned his MSc in chemistry in 1989 and completed his PhD in polymer chemistry from RTM Nagpur University in 2000. Currently serving as a professor and head Department of Chemistry at Kamla Nehru Mahavidyalaya, Nagpur, India. He has made significant contributions to various fields of chemistry. Throughout his research career, Dr. Gurnule has focused on the synthesis and characterization of nanomaterials, SBR nanocomposite materials, semiconducting materials, ion exchange resins, biodegradable polymers, conducting polymers, and epoxy resins. He has an impressive publication record with over 230 research papers in national and international journals and over 110 research papers presented at conferences. Dr. Gurnule is also a highly regarded reviewer for prominent international journals of Elsevier, Wiley, Springer, Bentham & Science, and RSC publishing houses. His dedication to teaching and research has been recognized with several awards, including the CRSI Best Teacher Award, the Distinguished Scientist Award, Aufbau International Outstanding Researcher Award, Best Researcher Award, ISCAS Prestigious Silver Medal Award, and Leading Educationist of India Award. He is actively involved in scientific societies and conferences, both nationally and internationally. Furthermore, he has been a mentor to numerous students, guiding 26 towards their PhD degrees and 21 in their MPhil research, and has even secured huge research fundings also. Dr. Gurnule's extensive involvement in science has been recognized by way of science articles for the public and research patents. Additionally, he has authored 32 books and 11 book chapters. Dr. Gurnule has a strong online presence with educational chemistry lectures on YouTube. His impact is evident through citations with a total of 1,312 and a respectable H index of 20 and I index of 40. Dr. Gurnule's global outreach is evident through his lectures, conferences, and visits to various countries, solidifying his reputation as a prominent figure in the field of chemistry. I humbly request you to please share your insights with us, sir.
Thank you, madam. Am I audible?
You are audible and your screen is visible.
Okay, the slides are changing. Okay.
Yes, sir.
So first of all, I thanks the organizer for invitation for this national symposium, and particularly I'm thankful to the vice chancellors of the university and also the Dr. Ashutosh Shukla and also the Dr. Kavita Sharma madam for inviting me for this national level symposium. And also I thank all the organizing team who are involved in this symposium. So today I am discussing about the functional nanomaterial which are useful in the service of mankind. So as we know, we are living in a dynamic world where the time domain and the geography are rapidly shrinking, but at the same time opportunities, and competitions and innovations as the key driver. As we know, science and technology are related to each other, but this knowledge-driven economy is mainly related to the materials. And as we know, in this case of material, uh, science is the pursuit of knowledge, and the technology is the creation of artifacts. So here, the development of many technology that makes our life comfortable are closely related to the material. That is, the material is very important, and there is a special branch of material where it is related, and we can know that it is the special branch which is known as the material science. And discipline of this material science So materials are of different types. And now we can say that science and technology solve the problems in order to understand the natural world. Also, we can say that science and technology solve the problem in order to improve the lives of people. Science and technology try to find out the causes of diseases and try to find out the cure. So material science and material scientists play a very important role in the development of country. And now scientists are rightly says that, especially the material scientists, they claim that 21st century is the century of material and especially the nanomaterials. Now, as we know, chemistry is the central science, which provides some fundamental understanding. We can also say that this backbone for sustainable development is the science and technology, and in which the chemistry is the central science. And we can say that now chemists invent and synthesize the molecule, and physicists characterize the molecule, biologists make use of these molecules, engineers fabricate the devices out of these molecules, and public enjoy this molecule in different forms. So this is the main, that is all this part is related to the material. And as we know, materials are the properties are different with the different size of that material. So here, next slide shows that if you go for the historical development, then we can say that here, initially there was the Stone Age was there, after that Bronze Age, and after that iron and advanced materials. And now we are in an age of this advanced material, modern materials, that is the, we can say, nanomaterials. So here is the so is the slide changing or not? Okay. So what is material? If anyone can ask the question, what is material science and engineering? So we can say that with the advancement of science and technology, so by using of these materials, what is the devices for the benefit of the society can be made, and where it is carried out in the, that is called the engineering. So there are the different parts of this material where the devices can be made. So this is the historical background of this material. And when we are related to the material, there are the four important process part. Four pillars are there. This blue color shows the four important pillars. One is the processing, that is where we have to synthesize the material. Second part is the structure, where we have to see the to know the arrangement of these subatomic or microscopic particle. Then we should have to know the properties. After that, what is the use performance of this material? And after making, it is also necessary to know the to characterize the material. So these are the four important pillars. And in this case now, it is also possible to make the composite. And for making composite, we can mix, we can take metal and ceramic to make the composite are polymer and ceramic, polymer and metal. So actually we know that composite material is a combination of two materials with the different physical and chemical properties. They can improve the strength and stiffness, and that is why it is possible to make like that. So in case of R&D, so in case of R&D, what is now, there are the three important, this triangle is shown, and three important parts are shown. One is here is the technology, which is market driven. Here is the competition driven, is the innovation, and scholarship driven is the science. So science, innovation, and technology, all these three are interrelated. And there is a important, all these three parts are very important in case of for the nation building, for research and development. Now, material scientists say that this material continue to change the world, and now as we are seeing day by day, new materials are coming. And what is now here? These new materials are using for different technology, and because of that, here, so we say that advanced technology, advancement in technology, science advancement, and material advancement. So because of this now, this material or technology and science create a continued advancement, and because of that, new things are coming day by day. And we see that things in the next slide also. So here, before going to see that, what are the application, here industrial revolution is there. So if you go to the change with the time, then after the middle age, steam engine came, railways and automobiles and computer. So after this, all these things, what is the next big step? We can say that is the nanotechnology. So nanomaterial, nanotechnology are both are very important, and because of that, we know this the advancement in this nanotechnology. Now, if you see the evolution in this nanotechnology, so from the if you see the year wise, so here is shown in 1970 there was some base research was there, and so this shows after around 2000, what is there? Applied research was there, and after that, early adapters, rapid advancement, and now after 2020 is the mass market of this nanomaterials or nanotechnology. Why the slide are changing?
Yes, the slides are changing.
How? Why the is it coming back? I don't know. So it coming back. This slide shows that one is scientist was there. That is the name is Robert Kerr. In IIT Hyderabad, he says that carbon nanoscience was much older as compared to carbon nano materials. So, and it is also observed that after analysis of some materials in the old ancient time, that is the Damascus sword of Indian soldiers, or we can say Maharana Pratap or Tipu Sultan, like that, Shivaji Maharaj. After analysis of that sword, it is observed that it contains some carbon nanotubes. And also, this shows that in the ancient time, glass material which was there in the Roman time, also having some coated, and that coated material was the nanomaterials. So it is this next I show the Agassiz cup, which is kept in the British Museum, and this is the Agassiz cup, which is the of the Roman pottery after 400 after Christ. So this red color in a light, and here is the daylight. So this red color, which is shown here, is nothing but the nano gold material. Already published this paper in the journal Nature. So here, this paper have been published. So we can say that this material was from the ancient time, not this is, but now we know from last 10 or 10 years that in what is the discoveries of different types of nano types of material and their technology, but this material was there, but people does not know about this material at the ancient times. Next slide, that is the what is nanoscience and nanotechnology. All of we know what is the particle size less than 100 nanometer in diameter is said to be a nanomaterials, and study of such material is the nanoscience. And related the technology which is related to that is nanotechnology. That means we have to make some devices. We have to make the design of this material of the desired size, and so that which is beneficial to the society and public. So these nanotechnologies span many areas. So here is shown where we can use the nanotechnology. So for the security, defense of food packaging, of agriculture science, medicine and health, so many areas are there, and particularly in the biotechnology also, or in medical field where the drug delivery can also carried out by using such type of material. So in case of the agriculture, now in our Maharashtra, one place is there in Karmeshwar, where by using this nano nutrient, they are giving the Israel technology was there, and they are giving in agriculture, so many land is there, and where they are supplying the micronutrient nanomaterials through that technology to the particular time for particular amount they are giving. So for this agriculture also, these materials are very useful. Why again this slide is coming? Slide is coming back.
Sir, might be there are some technical issues at your end. This could be the possible reason.
Why they're coming? This is first time. Okay. Now, as we know, nano size is a small. That is, nano is small, and small is a very powerful. And as we know, small is a sustainable also. And as all of you know, small is also for excellent performance. And a small rules large. And someone can say that is small is a beautiful. So this is the nano material, which is very beautiful material, and having a number of application in different fields. Again, in the food, agriculture, biomedical, environmental, for control the pollutions. We are discussing also this slide in next. What are the applications? And in also industry for different field. So these are the area where this technology or these materials can be used. Now, when we are dealing with this material also, there should be some what is a national or international level, some safety issues are there, and therefore, in case of R&D in industry or in the some of the laboratories, we should have to take some safety precautions or some health issues, so that we can solve the problem. Because this nanomaterial, we should also take some precautions with this material. Because it is dangerous if we inhale these materials. So that is why we should have to take care, and therefore it is suggested that national or international level is some there may be some we can say the some societies or some of the so that the issue can also be discussed. So in the point of the safety of the laborers or laboratory persons. Why this coming again back? What is the issue? Can I share again?
Sure, sir. Sure, sir. You can.
I'm stopping this sharing. Okay. Why this is happening? I don't know. Now it's visible now?
Yes, sir.
Hello?
Your slides are visible.
Okay. Now, in case of nanomaterials, there are two important approaches. One is a top-down and another is bottom-up. In case of top-down approach, this is given by the Richard Feynman. He is a physicist and also received the Nobel Prize in 1965 for giving there. He says that there is a plenty of room at the bottom. Again, the same thing is happening. I don't know. So he says that there is a plenty of room at the bottom. Another approach is given by the Jean-Marie Lane, and he has given the bottom-up approach. So start from the that is the small particles like atom, molecules, and molecules, so that we get the nanomaterials. So both the scientists have suggested, and secondly, Jean-Marie Lane says that there is a plenty of room at the top. So meaning of this, there is a plenty of room at the bottom and top. Meaning is that we can make as we like the compartment. So one part, suppose one room is there, it can be divided into two parts, and it can be divided into four parts by partition. In the similar way, we can make number of compartment in this small material, and therefore that is the beauty of this material, that they have a much more storage capacity. And now we can say that here, why another question anyone can ask, why do we want to make these things small? So as we know, all of we know what is, we make things small because it should be cheaper, smaller, faster, better, and easy to handle, and easy to carry from one place to other using different purposes. So also, and that is why the things are going smaller and smaller as the material we are using such type of nanomaterial. This slide show that how the material show the changes in the properties, show the nano in case of nano region. So some quantum mechanical behavior is shown, while what are the properties they are changing is shown here. If increase the surface area, what are the chemical processes? These are the properties where melting boiling point can be shown the changes. And here molecular recognition, and there may be a new bio applications, that is self-organization, repairability, adaptability, recognition. So because of these material changes, they show the changes in the size of material changes, they show the changes in the properties. So this is the slide that shows changes in material. And here it shows another slide that this is the slide where what are the, if the size of the material changes, these are the properties, they show the changes. Melting point, magnetism, all these are the properties. If the size of material change, the properties also show the change. And this next slide show how nano sizing causes the changes in the color. So as we know, bulk gold is a golden in color, having melting point and color golden. Bulk material, bulk golden. But when it is in a 1 nanometer size, it is a brown yellow color, shown here, smaller size. When it is 20 nanometer, then it is a red color. So gold is also a red in color if the size is 20 nanometer. Even melting point and lambda max is also different. When it is a 100 nanometer size, then they show the purple pink color. So see, the size is small, then slightly greater, then slightly more. So color also show the changes. So this shows that if the size of particle changes, the properties of the material also show the change. These are the solution of indium phosphorus, and this is the cadmium selenium. See, the pH is 4. Here, what is the size is 4, and different size is shown here. And show the different color, 4.4, 4.2, 4.8, 5.5 nanometer is size of the solution. See this orange type color and different. Just me, I'm checking. This slide show different area where these nanoparticles and particularly silver or gold nanoparticles can be useful for here anti-cancer activity, RNA delivery, for drug delivery, antimicrobial activity, and anti-blow film activity. So different types of medical field having these are the materials where we can use for the diagnosis, therapeutics, and nanomedicines like that. And this another slide show the chemistry, that is Professor C.N.R. Rao suggested that when the particle size is small, then when the reaction is carried out, then there is emission of carbon monoxide and carbon dioxide. When the similar reaction carried out with the larger size, then only there is emission of CO and only the CO, carbon monoxide. So we can say that nano size show the change in chemistry, which is shown here. And also this paper already been published in the European Journal in 2002. Next slide shows that why this is happening, I don't know. So this is the change of chemistry, and here these two approaches already we discussed, top down and bottom up. And the next is these are the different methods of preparation of this material, nanomaterials, and some more modern methods are given here. And in this case of modern methods, out of all these methods, hello, madam.
Yes, sir.
Something is there, I am stopping my sharing. Okay.
Okay, sir.
Okay. Again, I'm checking why it is there.
Could you please sum up your content without presentation?
Because it is coming back to the first slide.
No issues. You please sum up your content without presentation.
Okay. Because many times it's happened.
So technical issues can happen with anyone, anytime. So
No, it's coming back now. Why it is coming? Okay, in short, I will show the slide. Okay, if it is not coming back, this is final. Okay, otherwise I will sum up my presentation here. These are some methods, and the sol gel method is the important one. And some we are using also solvothermal and also hydrothermal methods. This is one of the method. Same thing is happening again. So different methods are there. I want to show some application, but it is very difficult to show the, because why I know the technical issues. Actually, there are single wall, multi-wall carbon nanotubes was also there. And there is one method that is known as CVD method. And after making that, we have to know whether it is single wall or multi-wall carbon nanotubes. And CVD method we are doing in a Sharda University, Greater Noida. And this CVD method is the most widely used method for this purpose of making these carbon nanotubes. Here I'm here in the slide. Mainly I want to know that I want to show you that the important application of these nanomaterials. So, three important material here I'm going to show you that is the nano zinc oxide. One is a nano silver, and another is a nano gold, and their applications. And finally, the application related to the magnetic properties, and some of the application related to the cement, and some of the applications related to the drug delivery in medical field, and also in what is the super capacitor or also super conductivity, and in the field of environmental science, and in the solar cell, and also in textile industry. So some experiments have been performed, and that I want to show, but because of technical issues, I cannot show the slide. Mainly the presentation is focusing on the synthesis of this material by different methods. And after that, we have to characterize by using the different methods like XRD, X-ray diffraction pattern, and after that, same TAME, and also the AFM, and after that, BT. So all these techniques we are using for characterization. And once we make this material, then number of applications are there related to the chemistry, related to the what is the photocatalysis, or related to the medical field or environmental science or in agriculture. Number of applications are there. Depending upon that, we have to study their properties, and we have to synthesize the material by different methods. With this, I am concluding my this presentation, because I don't know the technical issues why it is coming back. Thank you, madam.
Thank you, sir, for your thought-provoking presentation, in which you have wonderfully described how chemists, physicists, biologists, and people in general are codependent with respect to molecules. Now it's time for question and discussions related to the presentations.
Sir, I have a question.
Yeah.
So what are the challenges in scaling up nanotechnology production for commercial application? Can you explain?
I can repeat, madam.
What are the challenges? What are the challenges in scaling up nanotechnology production for commercial applications?
Number of challenges are there. We have to set the apparatus. First of all, what methods we are using. We should have to take some precautions also, because it is nano size. Okay, na? Some safety issues are there. Environmental issues are there, and okay, these are the main challenge in industry, also in the laboratories also. So we should also take the care. The person should be having the skill related to this material. He should know all these things.
See, the photocatalytic, water splitting has come to a very good technology nowadays.
Yeah.
Formation of this hydrogen fuel.
Yes, it can also be used. Yeah.
Thank you, sir. As there are no questions, so we are going to proceed further. To bring this enlightening technical session to a close, I would like to respectfully invite our chairperson for ANKURAN-2023, Dr. Ashutosh Shukla, to offer concluding remarks. Sir, the floor is yours. You are not audible. Please unmute yourself.
Thanks, Ujla. And first of all, I would like to express my greater thanks to Dr. Kavita Sharma, convener of this program, and our respected Guru Prasad sir for organizing very mind-blowing symposium. Definitely, it was very mind-blowing deliberations given by our all honorable speakers. Dr. Swaminathan has thrown light on the topic nanomaterials for energy and environmental, and the applications of the role of photolytic nanomaterials. He also deliberated on the fabrication of different types of photoreactors. Really, it was very, very wonderful and nice. And also he has given us an insight of solar photoreactors and also some removal of air pollutants. Then Dr. Naveen Chandra. Dr. Naveen Chandra has also deliberated and explained everything very nicely. In his introduction, he has very, very beautifully he has explained the nanomaterial by a pictorial graph. Then 1D nanofibers and their applications. Then electrospun fibers, he has deliberated all these things very nicely. Then Dr. Vasudev sir has also given us an insight on the topic functional nanomaterials in the service of mankind. Very nice, sir. And thanks, sir. Ujla, over to you.
Thank you, sir. To convey our heartfelt gratitude, it is my great pleasure to invite Dr. Namita Upadhyay, Assistant Professor, Department of Chemistry at Sri Vaishnav Vidyapeeth Vishwavidyalaya, Indore. Ma'am, please.
Esteemed speakers of the technical session, Professor of Chemistry, Nanomaterials Laboratory, International Research Center, Kalaslingam University, Dr. M. Swaminathan, Professor, Department of Chemistry, University of Mumbai, Dr. Naveen Chandra, Professor and Head, Department of Chemistry, Kamala Nehru Mahavidyalaya, Nagpur, Dr. Vasudev Gurunule, General Secretary, Association of Chemistry Teachers, Professor of Chemistry, Wilson College, Mumbai, Dr. D.V. Prabhu, Dean, Faculty of Sciences, Head, Department of Chemistry, Dr. K.N. Guru Prasad, Coordinator, Sri Vaishnav Institute of Forensic Science, Chairperson of the session, Dr. Ashutosh Shukla, Coordinator, ANKURAN-2023, Professor, Department of Chemistry, Dr. Kavita Sharma, respected HOIs, HODs, Co-Coordinator, ANKURAN-2023, Assistant Professor, Department of Chemistry, Dr. Supriya Vyas, faculty colleagues, students, and all the participants. Good evening to each and every one of you. On behalf of Department of Chemistry, Sri Vaishnav Vidyapeeth Vishwavidyalaya, Indore, I, Dr. Navnita Upadhyay, want to take a moment to express my deepest gratitude for the incredible chemistry symposium. First and foremost, I would like to extend my sincere thanks to our guest speakers, Dr. M. Swaminathan, Dr. Naveen Chandra, and Dr. Vasudev Gurunale, whose expertise and insights left a lasting impression on all of us. Experts have provided an in-depth analysis of advanced nanomaterials, elucidating their remarkable attributes and extensive array of potential applications. Their contribution enriched our understanding of latest development in chemistry and opened new avenues for exploration. I would like to express my deepest gratitude to the General Secretary, ACT, Dr. D.V. Prabhu, for his unconditional support and collaboration with ACT. Your passion for chemistry and commitment to nurturing the next generation of scientists is truly inspiring. Thank you, sir. I would also like to express my profound gratitude to Dean, Faculty of Sciences, Director, Sri Vaishnav Institute of Science, Dr. K.N. Guru Prasad, for not only giving permission to organize the symposium, but also for his moral support and guidance for the program. Thank you, sir. I extend my gratitude to Dr. Ashutosh Shukla, chairperson of the session, for his keen interest for dedicating his valuable time to be with us. Thank you, sir. I am also thankful to the coordinator, ANKURAN-2023, Dr. Kavita Sharma, for her tireless efforts in putting together this remarkable event. Her dedication and planning have ensured the smooth flow of the symposium. Thank you, ma'am. I would also like to convey my deep appreciation to co-coordinator ANKURAN-2023, Dr. Supriya Vyas, for her continuous, sincere hard work and diligent efforts in the planning and execution of the program. I extend my gratitude to the faculty members of the Department of Chemistry for their invaluable support and contribution. I would also like to acknowledge the work of our technical team who ensured the smooth conduction of the symposia. Lastly, I'm happy to express my thanks to all the students, other participants present here for paying attention and learning. As we conclude this event, let us carry forward the inspiration and knowledge we have gained today to make positive changes in our lives. Once again, thank you all for being a part of this event, and we look forward to future opportunities to come together. Thank you all. Over to you, Ujla ma'am.
Thank you, ma'am. There is an announcement. Feedback link is there in the chat box. Participants are requested to please fill the feedback link. And everyone is requested to please again switch off their cameras. Thank you so much, everyone. We hope that you found this symposium to be both enlightening and captivating. We eagerly anticipate your participation in our forthcoming symposiums, conferences, and events. Wishing you all a wonderful day ahead. Thank you so much.
Thank you, Ujla.
Thank you.
Thank you.
Thank you, sir.
Thanks to all.
Thanks to.
Thank you, team. Thank you for inviting us. Thank you.
Thank you for the opportunity given to us. Thank you.
Thank you all. Thank you, sir.
Somanathan sir, thank you.
Gurnale, how are you?
Yeah, thank you. Thank you.